You know, we call these sessions the modern Druids because they really are the ones thinking about the shape of futures to come. A lot of the discussions over the last 2 days, I'll just wait a minute till, the doors settle down. A lot of the discussions over the last 2 days has been about the need for man and the human race to progress, the satisfaction of our greed and of our aspirations, and how the earth can sustain that. Where will the energy come from? Yesterday, we had some protesters and activists from Kudankulam who were arguing that nuclear energy does not have to be the only option. And today, we have again one of the most foremost scientists from the UK, somebody who believes that there are options, somebody who is bent upon creating fusion energy. Please welcome Stephen Cowley.
If you want to say something romantic to somebody, you probably want to take them outside, and you want to stand under the twinkling stars. There's something about stars and starlight and that connection with the infinite that seems to be appropriate at those times. When we look up into the sky and we see these distant dots in the sky, we probably don't think immediately of what's going on inside them. I do. It's probably not an appropriate thing to do when you're discussing something romantic, to be sort of looking at it like this, and I speak somewhat from experience at this point. Stars are amazing things. The center of stars is at about, at the center of our sun is at about 15 million degrees, and it's a thermonuclear furnace. As I said, this is not an appropriate thing to discuss in a romantic moment, but a fantastic cauldron in which all the elements in your body are made. We haven't really known about this for all that long. This is a picture of the sun. The sun, please don't look at it like this. When you look at the sun through appropriate filter, you can see this spotty structure on its surface. Those are the magnetic field lines that are erupting from the surface. And you see these white hot bits on the surface. It's bubbling away because in its center, some really extraordinary things are going on. The story of our understanding of this is sort of what I'm going to talk about. I'm going to talk about how we can imitate the sun, how we're actually doing it in our laboratories now, and how in the future we would like to power a great deal of the planet using the same processes that the sun uses. And the story really starts almost 100 years ago. Sir Arthur Stanley Eddington was probably the greatest theoretical astronomer of his time. He had made his name both with mathematics and with an expedition to South America in 1917 to measure the bending of starlight around the sun and confirm the predictions of Einstein's theory of relativity. And in 1920, he was the president of the British Association for the Advancement of Science, and he was to give the presidential address. And in 1920, he was starting to think about what's going on inside stars, and particularly what's going on inside the sun. Because the sun, being the nearest star to us, is probably the one we should try and understand first. And he realized there was something staring in our faces that was very strange about the sun. 60 years prior to this, the then theory of the sun was that it was a great big ball of gas collapsing in on itself, and as it collapsed, it got hot, and as it got hot, it radiated away its energy, and it collapsed still further. And Lord Kelvin, the great Scottish physicist, had said, well, this means that the sun is probably 10, 15 million years old. He did a little calculation. And Darwin was very upset about this. This wasn't enough time. But it was the prevailing theory of what the sun was doing even in 1920. And Eddington got up to give his address, and it's one of the most marvelous addresses in all of modern science. You can read it on the internet. He got up and he said, you know, it's staring in our faces. That can't be what's going on in the sun. He said there must be some power source at the center of the sun, because the sun can't only be 10, 20 million years old. It must be billions of years old, because he listed all the evidence for that, and I won't take you through that, but he said it must be billions of years old, so why is it still hot? If it was just cooling down, it would have cooled down years ago. And so he said there must be some power source in the middle of the sun. Now, in 1920, we didn't really understand what the atom was really made up of. We knew there were electrons going around and there was a charged center, but we didn't really know what was going on in there. But just prior to this time, a guy called Aston had measured very carefully the masses of the elements. So he had something called a mass spectrometer, and he measured the mass of hydrogen, and he measured the mass of helium, and he pointed out that Aston didn't, but he just measured them. But Eddington looked at this data, and he said, aha, I think I know what's going on. He said, look at this. The mass of helium is a little less than 4 times the mass of hydrogen. In fact, the mass of hydrogen in atomic units is 1.008, and the mass of helium is 4. So if you could take 4 hydrogens and somehow put them together, take the nuclei of the hydrogens and somehow put them together and make helium, you would have a little mass left over. And as I said before, Eddington was sort of the greatest relativist apart from Einstein of his time. And he said, if there's a little mass left over, mass is energy. E equals mc squared. And so he calculated how much energy you would release by turning hydrogen into helium. And he said, this is phenomenal. I mean, you can read this. He doesn't use the word phenomenal. But if you took 1 kilogram of hydrogen and turned it into 4 kilograms of, 1.008 kilograms of hydrogen and turn it into 1 kilogram of helium, you would release enough energy to power your life for 10,000 years. That's just 1 kilogram. He said, this is phenomenal. This is huge amounts of energy. And he said, this must be what the sun is doing, because he's looking at the sun and he says, yes, there's hydrogen in there, there's helium in there. And so what it's probably doing is converting hydrogen into helium. And he sat down and then he calculated what he thought the age of the sun would therefore be. He said, supposing the sun converts 1/3 of its hydrogen into helium, and it's done it for how long in order to keep shining? And he came up with 15 billion years. And that's much more like it. In fact, it's quite a good estimate for the lifetime of the sun. It's more like 10, but within the accuracy of what he was doing, it was pretty phenomenal. And he didn't worry about any of the details of how it did this. He just said, this must be what the sun is doing. And indeed, it is what the sun is doing. We spent a long time working out the details of it, but Eddington was right. And he went on to say, this reservoir can scarcely be other than the subatomic energy, which it is known exists abundantly in all matter. We sometimes dream that man, these were very sexist times, will one day learn how to release it and use it for his service. The store is well nigh inexhaustible, if only it could be tapped. Well, this is 1920, and it's a long time ago. But Eddington was looking at this and saying, this must be a phenomenal way to power our lives in the future. And we've been trying to do it for about 60 years now in real earnest. So 100 years ago, he postulates that this process will happen. About 60 years ago, we started to try and do this. And what I'm going to tell you about is that we are just about doing it, and we're just about to master it. And this is a phenomenal experiment that we're building in southern France. This is a picture of it. Obviously, it's not built yet, so you can see the standard-sized person standing beside it. It's an enormous object. If you look at the yellow enclosure is a donut-shaped enclosure, and it's surrounded by powerful magnetic fields. And in that donut-shaped enclosure, we are going to confine the fusion fuel. Because this process, the process of taking little atoms and building them up and making bigger nuclei of atoms is called fusion. And we can extract energy from this process in phenomenal quantities. So what we're going to do in this experiment, in that yellow enclosure, is we're going to heat the fuel up to about 200 million degrees. And at 200 million degrees, it will be like the center of a star. It will be a little star on Earth. And at 200 million degrees, all the nuclei inside there will be smashing into each other and fusing. And they will release energy. And so in this experiment, we are going to demonstrate for the first time what we call a fusion burn. Let me show you. I'm a physicist, so I love showing graphs. So I'm sorry about this, and it's just before lunch, and it's nuclear physics, and you're going, what the hell? So if you look on this side, what we're going to do is we're going to turn the machine on, power up those big magnetic fields inside the machine, put the fusion fuel inside, and at this moment here, this is seconds along the bottom, we're going to start to heat that fuel up. And this blue patch here, greeny blue patch here, at about 80 seconds in, starts to heat the fuel. Now what happens at that point is the fuel gets excited up to about 200 million degrees. And it's held by these magnetic fields in this cage of magnetic field in the center, and it starts to react. And what you can see here, and I always talk about the red line because it's the most optimistic, these are computer simulations of what would happen. You can see in the red line the power coming out of this hot, what we call a plasma, shoots up. And on this side, this is power in megawatts. So this is what our experiment will do. This experiment will heat it up to 200 million degrees. It'll start fusing, and we will see fusion power come out at about 500 to 600 megawatts of power, about half the size of a typical power station. And then at 400 seconds, we will turn off the heaters, and it will sustain itself. We will have made a little star on Earth. Now, this experiment is a collaboration between more than half of the world's population. Mastering this science, mastering this technology is so important that more than half the world's population have come together to build this experiment. We're building it in rather a nice place, actually, southern France, but in Provence. I'm hoping to spend many years in Provence. You can see along the top the flags. India is a key player in this. There's a very important lab up in Ahmedabad doing some of the key work to construct this device. And you can see, the Americans, the Japanese, the Chinese, the Europeans. We're all collaborating on this. Because once we can master this technology, it's going to make a profound difference on the planet. And I'm going to explain that to you. So, why are we going to do it? What are we going to do it? How are we going to do it? And most important, when are we going to do it? We've been trying for 60 years, and it's been really hard work. When we first started, we couldn't make any fusion reactions at all, and now we're beginning to make them in experiments in my lab. And in the future, we want to make your electricity with this. Why? This is one of the most telling graphs about energy consumption. Along the bottom is the GDP per capita. Basically, how wealthy people are in countries. On the left-hand side is energy consumption per capita, per person. It's tons of oil equivalent. And there's this very strong correlation between wealth and energy use. Now, you might say we have to break this cycle of this correlation, but it's there. And it's very, very hard to break. And if we're going to lift 1 billion people out of poverty, we're going to have to provide them with energy. We're going to have to provide them with energy, and we're going to have to provide them with energy that's cheap and available everywhere in the world. And this is one of the biggest challenges we have completely over the next few years. Right? What you can see on this graph, you can see the USA up there, almost the biggest user of energy per capita. Canada is a bit more because it's colder and distances between towns a lot longer in Canada. But you can see most of the world is right down in the bottom left-hand corner here. Most of the world is not getting its share. And we have to do something about that. It's not fair, and it's not stable. Predictions are that by 2050, 2060, and again, all these predictions have large error bars in them, and you don't really quite know exactly what it's going to do. But by 2050, we will have something like doubled to tripled our energy consumption in the world. Now, I'd have said 4 or 5 years ago, and I certainly did say 4 or 5 years ago, right, that the big challenge at this point is to wean ourselves off fossil fuels. Because we've been worried about global warming in the scientific community since the early 80s. The big challenge is to wean ourselves off fossil fuels and raise people out of poverty at the same time. Because what's happening in the world at the moment, particularly in the United States, is that the price of fossil fuels is being driven down by new exploration, by new finds, by shale gas. The price of gas in the United States at the moment is so low that companies are flooding into the United States in order to take advantage of this incredibly low cost of fuel. And what I've plotted here is for the major, these are the fossil fuels, oil, gas, and coal. This is uranium, as in normal nuclear power, breeders, which is a more advanced kind of nuclear power, and lithium, which is the basic fuel for fusion. I'll come on to that in a moment. I've plotted it on the left-hand side, the number of years' worth of the world energy demand you could actually supply with these fuels. Now, what's happened is that the world has decided that the cheapest way to power the world is to use these fossil fuels faster and faster. We're seeing increasing use of gas, increasing use of coal, and those of us in the scientific community are starting to despair that we will ever turn around this juggernaut of fossil fuel use. We do not want to see the world warm up by 6 degrees, but these are the cheap things. And in times of recession and when the economy is hard in the world, everybody is flooding towards them. So the answer, I mean, there are political answers, and I'm not a politician, so I'm not going to approach that. The answer for the scientific community is that we have to replace them with things that are cheaper. If we're going to get in there, we have to have fuel sources, power sources that are cheaper than the fossil fuels, so we stop using them. Because if we use all the fossil fuels that are left to use, we will fry the planet. Now, on this right-hand side is lithium. And lithium is one of the basic fuels of fusion. And lithium comes in 2 places. You can get lithium in the high Andean deserts out of what's called salty brines, or you can extract it from seawater. And we now have a process to extract it from seawater, and that gives us this line here. This line here is the amount of lithium we have if we powered the world by fusion. It's 30 million years worth of use. It's an unbelievable store of energy, and it's in the ocean. Right? It's in the ocean just down there. again, as a scientist, there are many things that will help us power the planet in the future. Wind, etc., right? But there are three sources that can really replace the 80% of our fuel that's given by fossil fuels. And that is these three. It's fusion, which I'm talking about. It's fission, if we go to advanced kind of reactors called fast breeders, which have some issues with them. And it's solar. And at the moment, all three of these are in need of serious research. So we have a lot of work to do. We can't immediately replace the fossil fuels because we don't have a cheap alternative. What is fusion? Well, the reaction we do is not the one that Eddington talked about. Eddington talked about taking ordinary hydrogen, putting it together, and making helium. It turns out that's actually very slow fusion. It's one of the most difficult fusion reactions to do. The reaction that we want to do is between deuterium and tritium, which are two exotic kinds of hydrogen. Deuterium is what's the hydrogen in heavy water. It's called heavy hydrogen. And you can extract it from seawater. It's 1 part in 6,000 in seawater. And so deuterium is readily available to us. Tritium is super heavy hydrogen. And it only lasts for about 12 years because it decays. And so you have to make it by bombarding lithium. So the reactions we want to do is we want to fuse deuterium and tritium, put them together, and when you do that, you make helium, and you get a neutron out. And the neutron that comes out flies off, and you arrange it so it hits some lithium, and when it hits the lithium, it makes the tritium, which you then take, this tritium, and you put it back in your reactor, and so your fuels are deuterium and lithium. And deuterium is so abundant, we never worry about that. And as I said, lithium, there's about 30 million years worth. Now, what's the problem? This looks great. Well, the problem is that in order to get them to fuse, is that they repel. They're charged. Both of them are positive charges. And if you want to bring them together, they repel and they repel. So the only way we know to get them together is to ram them together really hard. And you can't pick up a nucleus and another nucleus and ram it together. So what you do is you heat them up so they're moving about really fast. They're moving about in random ways. And typically what will happen if they move about in random ways, they will come close to each other and do something like this. So here's tritium coming from the right, deuterium from the left, and they just bounce off each other. But if they happen to be randomly moving head-on and fast enough, they'll do this. And at that point, they fuse. They've got to get close enough so that the force that binds them together, which is called the strong force, which only acts when they get very close, grabs them, makes helium, and spits out a neutron. Well, it turns, in order to make that happen, you've got to heat up the deuterium and the tritium to about 200 million degrees, and you can't put that in a bottle. So what we do is we make a cage out of magnetic field. We put magnetic fields around it, we push on it, we hold it off the walls, and then we heat it up, as I showed you in that first graph. We heat it up. When it gets to the temperature 200 million degrees, it starts to fuse. And it sounds absolutely incredible, but we've actually done it. Here's a picture of the machine in my lab. My lab is about 10 miles south of Oxford in the UK, and we run the world's only device that can actually do any fusion at this point. And we're about to do some new fusion shots in 2015, which will be the preparation for this machine in France. This was a famous shot that we did in 1997, time along the bottom here, and this blue line here, for 2 seconds, not very long, we hit 16 megawatts of power. We were having to heat it with about 20 megawatts of power. So actually, the 16 megawatts was the extra power we got out. So we got 36 megawatts of power out. We put about 20 megawatts of power in. This was the first time we'd actually demonstrated. This was Eddington's vision, that we can actually do what stars do in the Earth. Then what? Well, we've got to move this forward. If the experiment in France is successful, it'll be successful by about the middle of the 20s. And if we can actually do what I showed you on that graph, which is light the fusion fire, have it burn, make 500 megawatts of power, then what we have to do is we have to build our first power station. Now, the Chinese have a plan that they might build a power station by 2030. But in Europe, we think we don't have enough cash, or perhaps we don't have enough political will, that we will do it by 2030. So we're looking more at the first electricity from fusion coming in at about 2040. And that will be the first time we actually do it. And then probably by the second half of the century, we'll start to eat into the electricity market. Is it competitive in cost? Well, my engineers had a look at this. And you can take this with a pinch of salt, because of course I'm a fusion nut, right? But we looked at what it would cost to build those reactors, once we actually mastered the technology. And we think we can bring the cost of electricity in comparable to wind, to nuclear, current nuclear, the way we do nuclear right now. This would be fantastic. It gives me hope that we're actually on the right track now, that we're going to get there by the middle of the century. It's perfect energy. It's perfect energy in every way. It turns out there are no runaway reactions. There are no nasty accidents that can happen from this. It doesn't produce any long-lived radioactive waste, right? It uses minimal amounts of land, and we have 30 million years worth of it. The real problem, it's not perfect in every way. It's really hard to do. But we should do it.